All these terms have technical meanings in physics, which are only more or less analogous to the meanings of the terms in popular talk. For the present, we are concerned with the technical meaning of energy. Throughout the latter half of the 19th century, a great deal was made of the conservation of energy. This principle was not easy to state in a simple way because of the different forms of energy. But the essential point was that energy is never created or destroyed, though it can be transformed from one kind into another. The principle acquired its position through Joule's discovery of the mechanical equivalent of heat, which showed that there was a constant relationship between the work required to produce a given amount of heat and the work required to raise a given weight through a given height. In fact, the same sort of work could be utilized for either purpose according to the mechanism. When heat was found to consist in motion of molecules, it was seen to be natural that it should be analogous to other forms of energy. Broadly speaking, by the help of a certain amount of theory, all forms of energy were reduced to two, which were called respectively kinetic and potential. The kinetic energy of a particle is half the mass multiplied by the square of the velocity. The kinetic energy of a number of particles is the sum of the kinetic energies of the separate particles. The potential energy is more difficult to define. It represents any state of strain which can only be preserved by the application of force. To take the easiest case, if a weight is lifted to a height and kept suspended, it has potential energy, because if left to itself, it will fall. Its potential energy is equal to the kinetic energy which it would acquire in falling through the same distance through which it was lifted. We can determine accurately the change of potential energy in passing from one position to another, but the total amount of it is to a certain extent arbitrary, since we can fix the zero level where we like. Both the kinetic and the potential energies of a given set of bodies will be different for different observers. In classical dynamics, the kinetic energy differed according to the state of motion of the observer, but only by a constant amount. The potential energy did not differ at all. Consequently, for each observer, the total energy was constant, assuming always that the observers concerned were moving in straight lines with uniform velocities, or, if not, were able to refer their motions to bodies which were so moving. But in relativity dynamics, the matter becomes more complicated. The Newtonian ideas of kinetic and potential energy can, without much difficulty, be adapted to the special theory of relativity, but we cannot profitably adapt the idea of potential energy to the general theory of relativity, nor can we generalize the idea of kinetic energy, except in the case of a single body. Therefore, the conservation of energy in the usual Newtonian sense cannot be maintained. The reason is that the kinetic and potential energies of a system of bodies are inherently ideas which refer to extended regions of space-time. The very wide latitude in choice of coordinates and hilly character of space-time combine to make it very awkward to introduce ideas of this sort into the general theory. There is a conservation law in the general theory, but it is not as useful as the conservation laws in Newtonian mechanics and in the special theory, because it depends on the choice of coordinates. We have seen that independence of the choice of coordinates is a guiding principle in the general theory of relativity, and the conservation law is suspect because it conflicts with this principle. We stated that in relativity theory, measured mass and energy are regarded as the same thing. Having discussed energy, we can explain why. Einstein's theory offers a formula allowing the measured mass of a particle to be calculated from its proper mass and its speed. The kinetic energy of the particle can be calculated according to the usual Newtonian formula. As we said, the 0 point for measuring energy is arbitrary. It's change of energy that matters. So we can add any constant quantity we like to our expression for the energy. If we do that, we can create an expression which, for velocities small compared to the velocity of light is the same as Einstein's one for the measured mass. So we have shown that energy and mass are equivalent. We now need the notion of action, important in relativity physics as well as in the quantum theory. The quantum is a small amount of action. The word action denotes energy multiplied by time. That is to say, if there is 1 unit of energy in a system, it will exert 1 unit of action in a second, 100 units of action in 100 seconds, and so on. Since energy is the same thing as measured mass, we may also take action to be measured mass multiplied by time. In classical mechanics, the density of matter in any region is the mass divided by the volume. In relativity mechanics, we always want to substitute space-time for space. Therefore, a region must no longer be taken to be merely a volume, but a volume lasting for a time. So, for a given density, a small region contains not merely a small mass, but a small mass multiplied by a small time. That is to say, a small amount of action. The postulate that a freely moving particle follows a geodesic may be replaced by an equivalent assumption about the action of the particle. Such an assumption is called a principle of least action. This states that in passing from one state to another, a body chooses a route involving less action than any slightly different route. Again, a law of cosmic laziness. Principles of least action are not restricted to single bodies. It is possible to make a similar assumption which leads to a description of space-time as a whole, complete with hills and valleys. Such principles, which play a central part in quantum theory as well as in relativity, are the most comprehensive means of stating the purely formal part of mechanics. We have been dealing hitherto with experiments and observations, most of which concern the Earth, or the solar system. Only occasionally have we had to reach so far afield as the stars. Now we shall see what relativity theory has to say about the universe as a whole. A few preliminary explanations about the general appearance of the universe are necessary. Much is now known about the distribution of matter on a very large scale. Our Sun is one star in a system of many millions of stars, called the galaxy. The galaxy is shaped like a giant Catherine wheel, with spiral arms of stars coming out of a bright central hub. The Sun lies in one of the spiral arms of stars, probably about 28,000 light-years out from the center of the hub of the galaxy. On the galactic scale, distances are often measured in light-years. A light-year is the distance which light travels in a year. The outlines of the galaxy are not at all sharp. The main body of stars is about 120,000 light-years across. But besides stars, the galaxy contains a great deal of gas, mostly hydrogen, and dust, as well as other material not yet identified. The whole accumulation of stars, gas, dust, and unidentified material rotates slowly round the hub. The galaxy is by no means alone in the universe. It is one among many millions of similar systems, scattered throughout the region which our telescopes can explore. The other systems are also called galaxies, or sometimes nebulae. Some galaxies are flattened, with spiral arms like our own. Others are round, like footballs.